So welcome everyone. Thank you for coming. Before we start, I'd really like to know who here is a developer? Okay, and who's a blockchain developer? Okay. So obviously this is the trend, this is where we're going, right? And that's why you guys are here. Thanks for coming. Okay, firstly I'd like to introduce Suraj. He's the attorney here, one of the attorneys here at Shepherd Mullen. He's a patent attorney. He's just going to have a few words. He's been kind enough to host us tonight.
Hi everyone, my name is Suraj Hussain. I'm an intellectual property lawyer here at Shepherd Mullen. Over the past year, we've been sponsoring events with FinTech Silicon Valley directed to blockchain technology and cryptocurrencies. And today's event is a continuation of that series. And we'll focus on Ethereum and smart contracts. And this area is of particular interest to us as a law firm because we want to leverage it in our practice and better service our clients. So thank you for being here, and I'll give it to Pema.
Thanks. If anyone wants to speak to Suraj, you could see him after the event?
Yeah, I'll leave some cards as well.
Okay. I'm going to pass it over now to David. David Goldberg has been kind enough to bring his expertise on the blockchain tonight to educate us all. Probably won't educate me much, but all of you guys I'm sure are smart enough. And he's going to walk through the basics of Ethereum. And if you're a little bit more advanced, don't hesitate to ask questions because he's happy to answer those as well. So over to David. Thank you, David.
Thanks, Pema. So, hello everyone, I'm David Goldberg. I'm a software engineer at Salesforce, where I've been for the past 2.5 years. And I got into Ethereum development because I found cryptocurrency really interesting. I think it challenges a lot of what we've come to know as traditional software. And it's got a lot of use cases around trust, so not just financial transactions, but it's sort of challenging the way that a lot of software to date has been written. What did I do to get up to speed? I started reading the Ethereum white paper, so that's probably the first thing I would suggest people do to get involved with and get some knowledge on Ethereum, especially if you already have some programming experience. It should give you a really clear description of the important stuff, and then which we'll cover a lot of today. And then also just reading documentation. So Solidity is the main programming language that people use to develop on the Ethereum network, and so we'll look at some Solidity code today. But the documentation is pretty good, so take a look at that. And then the other thing I think is just to start programming. So at the end, I'll include a link to a sample smart contract. It's called DApp, is an abbreviation, standing for a decentralized application that my partner and I created. So there's a blog post walking through how we did it, and so hopefully you'll find that valuable as well. So before we get too far into it, I'm just going to skip ahead to the end. The top link is that link. So if at any point in time you find what we're covering today to be too basic or too boring, or you're not feeling challenged, give that a look. But only if you feel like you already know the stuff we're covering and that it's not doing it for you.
Will you upload the slides after?
Yeah, I'm sure. I think that's probably a question for Pema or the organizer, but we'll make sure that you'll have plenty of chance to get these slides, and you can contact me anytime I can send them over as well. So my contact info. So that's the top link, is if you find this too basic. Right. Anybody want to take a picture before because it's gonna go off the screen, so real quick, and so the goal of today is going to be to give you a strong foundation so you can go out and build Ethereum dapps and smart contracts. Obviously there's so much stuff to cover, and we only have so much time, so we're probably not going to get to address everything, but hopefully it'll give you a good enough foundation and building blocks to get started on your own. All right. So we're going to talk a little bit about what is a blockchain. We're going to keep that pretty brief. And then I'm going to talk a little bit about Bitcoin. The primary purpose, of talking about Bitcoin is to then contrast it with Ethereum, kind of give some differences as to what are the main ways that Ethereum is implemented versus Bitcoin, because they both use a blockchain implementation, just do things differently and are used for different purposes. And then, obviously we're going to talk about Ethereum itself. It's the most widely used network for smart contract development. And does everybody here know what a smart contract is? Can I get a show of hands? Does anybody not know? You're definitely not alone. So a smart contract is essentially an automated, contract by the name of it, that will run in the blockchain and can basically execute against any set of rules. And once those rules are satisfied, it will send value, in this case Ether, when we're talking about Ethereum, from party A to party B, or from party A to multiple other parties. So the idea is it's automated, and you can write whatever rules you want. So it's fully customizable in terms of the logic. So that's an important thing. And then the term dApp, like I mentioned, is used to represent a decentralized application. We'll look at a slide that talks about the architecture of the back end of what a dApp is and how that's different than a centralized application. So, centralized application, think of your favorite website. That's a centralized application. And so we're going to talk about the computing environment. So how again is the actual computing environment where code runs, how is it different than when you interact with a website and there's server code running, maybe it's hosted on Amazon Web Services or something like that. How is that different than how Ethereum runs code behind the scenes on the back end? And then we're going to talk about Solidity. So we're going to look at some actual code and a couple sample smart contracts so you can get a sense of what the syntax looks like. Is anybody here familiar with JavaScript? So the syntax of Solidity is pretty similar to JavaScript. There's not that much different. Obviously, the inner workings and what's happening behind the scenes is a lot different, but the actual syntax itself isn't too bad. And if you already have some JavaScript experience. And then Truffle. So Truffle is a development framework. It's basically, anybody here heard of a CLI tool, command line interface? So when you're programming, it'll save you a lot of time. So Truffle will make it so you don't have to interact with the blockchain directly, because that can be sort of a time suck or somewhat confusing from a developer's perspective. So it does a lot of the things for you that you don't need to worry about, so you can just get up to speed and start writing code much quicker. So take a look at that. One other resource that I would recommend taking a look at is CryptoKitties. I'm not sure if anyone's ever heard of that, but their Solidity code is actually pretty great, and it's pretty easy to follow. So just in like 2 or 3 hours of looking at their documentation and their code, that might help you get a lot further along. So I would definitely recommend that as a resource. I have the link at the end of the presentation. So, okay, great. So what is a blockchain? We're going to sort of treat it like a black box for most of today's talk. So sort of already assuming you know a little bit about what a blockchain is, but I definitely want to paint an abstract idea just so you have a sense of it and can relate the stuff we talked about in terms of Ethereum to it. So basic understanding is important. So it's a distributed ledger. It's a append-only log, so you can't actually delete things or modify things. You can write to it. You can write to the blockchain. You can say, hey, I'm going to create a new smart contract and put it on the blockchain. But once it's on there, it can't be it can't be updated, and it cannot be deleted. And so, like, let's say I deploy a smart contract to the network, and I decide, oh, there's something wrong with it. You can't just update the contract. You have to actually say, I'm going to deactivate this contract. Nobody's going to be able to call it anymore, and then redeploy a new contract. So that's somewhat burdensome, but again, there's trade-offs in terms of decentralized versus centralized. And part of the ability of it being decentralized is nobody should be able to decide, this contract needs to be updated, basically. Or like another example would be, let's say a smart contract incorrectly sent money from party A to party B. Who's going to decide how to undo that, right? As soon as someone can undo that, we're now dealing with centralization. Because if I can decide how it should be undone, then I'm the party who's sort of the centralized owner and I'm in control. So there's definitely trade-offs between decentralized and centralized applications. So blockchain doesn't always make sense for every use case. It's definitely applicable to a lot of use cases, but that's one of the things I've found is a lot of times people will be like, oh, we have this use case, we want to build a blockchain for it, or we want to use blockchain, and then it may not actually make sense. And we'll talk about some other examples of why. So blockchain, it will help keep track of ownership. So you have this decentralized ledger. So what makes it decentralized is that there is a consensus. The network agrees who owns what. So look at Bitcoin, for example. If I have my private keys, and I send my private key and I want my Bitcoin, the whole network's going to agree, yes, I own the Bitcoin and I should get the Bitcoin. And so what makes that important is the idea that the whole network agrees. So that's where this idea of trust comes in. So if I try to scam the system, let's say I try to say, I'm pretending to be that gentleman and I want his Bitcoin, the whole system has to agree that I'm actually that gentleman. And so even if I trick one of the nodes in the network that I am, all the other nodes are gonna be like, no way, you're not him, so we're not gonna give you the Bitcoin. So they have a consensus and they agree on who owns what, essentially. So let's talk about Bitcoin for a sec. So Bitcoin was the first mainstream cryptocurrency. And when it first came out, the white paper basically said it's a form of electronic cash, so a way for people to transact in that decentralized nature, and it's implemented by a blockchain. So classic example is I go to pay someone else, they have to trust that I have the money to actually pay them, otherwise the transaction won't go through. They have to trust that my bank has the money. So all of this brought to the blockchain will really help streamline that process. Some of the, downsides of Bitcoin itself is you have limited programmability. So you can run scripts, but you can't do all that much stuff. And a lot of it is just to send a transaction from someone saying, I'm getting paid in Bitcoin. Whereas when Ethereum comes in, smart contracts are customizable code. So you can write your code to do pretty much whatever you want to do in terms of your own logic. There's certain limitations, which we'll also talk about. And so you can see on here, so Bitcoin is not Turing complete. Anybody here know what Turing complete means? So the idea of Turing complete is theoretically this program will find an answer to a computational problem eventually. So an example for that would be, anybody heard of Java? So Java runs on this, it's called a JVM, it's a virtual machine. And so as long as you have a functional JVM on your computer, the computer will run Java code and it will eventually find an answer to a computational problem. But there's no guarantees that you may hit like networking issues or something like that will prevent the code from running. But a Turing complete language means it will take in a computational problem and theoretically eventually find the answer. So Bitcoin is not Turing complete, whereas Ethereum is. So it's one of the main differences. And Bitcoin is primarily like the scripting, the programmability that I was talking about. It's mainly used for like multi-sig use cases. So multi-sig would be, it stands for multi-signature. And essentially, let's say we have 3 people who are co-founders of a company, and they want to be able to control when the company pays expenses. But they don't, let's say one of the 3 people goes out of town regularly, they don't want to have to be burdened by when that person is out of town, like if all 3 people need to approve on the expense that we're going to send for payment, then it might be burdensome for the company. But at the same time, they don't want one of the 3 of them just to be able to run away to Mexico with the money that they're supposed to use to pay expenses to other people. So as a result, they create a multi-sig wallet. They say, in order to send money, we require 2 out of the 3 signatures. And then all of this is automated via Bitcoin's blockchain. And so this can be programmed into Bitcoin. Whereas that's probably the main use case, and you're much more limited than what you can do with Ethereum. All right, so we've learned a little about Bitcoin. Most of you probably already knew a lot of that stuff, but I just thought it was important to just acknowledge. And so a few big differences between Ethereum and Bitcoin is, first so they both use what we talked about, consensus, right? How does the network agree that someone owns something or something is in a valid state? And the way that they do that and the way that's possible is through this idea of proof of work. So anyone here heard of mining Bitcoin? Right? So essentially, Bitcoin miners get compensated for solving computational problems where essentially they are verifying transactions that occur on the blockchain to be valid transactions. And those get grouped into what's called a block. And so Ethereum's proof of work was specifically designed to, anybody heard of an ASIC chip? Anybody know what that means? So if you've heard of ASIC, it's application specific integrated circuit. So anybody here familiar with NVIDIA? So they make chips that run on GPUs, and other companies make chips that run on CPUs. The idea of an ASIC is it's a piece of hardware that is designed to use software for a very specific thing. So like we want to maximize some resource that the computer uses, so we're going to design this chip to be very specific, only for this one use case. And if other use cases try to use this chip, they probably won't perform as well as a GPU chip or a CPU chip or something like that. So Ethereum, realizing that people could make chips to basically try to do Ethereum mining, they view this as a centralized thing. So they wanted to basically prevent people from being able to say, we're going to make chips specifically for the purpose of mining Ethereum. And so this is something that I think got a lot of thought. And so what they did was they decided to make like what will help you mine Ethereum, not based on like CPU power or not based on computing power itself, but based on how fast you can move data around in memory. And so because of that, let's say what's really good for moving data around in memory is like gaming chips. So GPUs is an example. And so if I can make a GPU chip that's really good for mining Ethereum, I'm actually more incentivized to sell it to a company like NVIDIA or use it for gaming or something like that, because there's way more upside in how much money I can make from doing that. So they basically like wanted to make sure that people weren't incentivized to build chips for mining that would sort of make it like I could hog these chips and become like this centralized miner where I'm now able to mine more Ethereum than you can. Does that make sense? So we can talk about that for a while. I mean, it gets pretty nitty gritty, but I think it is an important distinction to make between Bitcoin and Ethereum in terms of the proof of work function. And so another big part of this here. So block size. So block size is a big difference. On Bitcoin, a block size is specified as 1 megabyte, whereas on Ethereum, it actually constitutes how complex the code is. So when you run code on Ethereum, you actually have to pay for that code to run. There's a transaction cost. Anybody ever heard of gas? So when you run Ethereum code, so all the resources to run this code, it's a shared network. So the resources are shared on the network, and to avoid someone from being able to hog resources, basically Ethereum said, we need to limit the ability to say, why should I be able to run more code than you can? I mean, if I'm willing to pay for it, then sure, but I'm not really incentivized to run a lot of complex computational power because I have to pay for it. So that's one of the differences as well. So on Bitcoin, there's a block size of like a megabyte, whereas on Ethereum, it's based on how complex your code is. Any questions so far? Making sense? So another big difference is block time. So in Ethereum, the average time between generation of a new block is about 10 minutes. Sorry, other way around. In Bitcoin, the average time between new blocks being created is about 10 minutes, whereas in Ethereum, it's about 15 seconds, so it's a lot faster. And so this helps with like the transaction speed. Like I don't know if anyone's ever sent Bitcoin from one address to another, or Ethereum from one address to another. The Ethereum will typically show up faster. New blocks get created much more frequently. And then we talked about the scripting, right? So Ethereum can actually run smart contracts that contain complex logic. They can do a number of things, whereas Bitcoin, yes, you can run scripts, but they're much more limited. Transaction costs, so they sort of, Bitcoin doesn't use like a varying cost by complexity model, whereas Ethereum does. And then mining rewards are a little bit different. So when you create new blocks in Bitcoin, you get 12.5 Bitcoin for basically, like as a miner, you solved the problem to create a new block. And so you get 12.5 Bitcoin. But then for every 210,000 blocks created, the reward gets cut in half. for the block, for Bitcoin. And so Ethereum gives no restriction to like halving. They don't, if tons of new blocks are getting created, they're not going to cut the reward for how much you get rewarded for a block. And that's currently 5 new Ethereum per block. There's also orphan and uncle blocks, which are a little bit, I don't think it's in scope for what we're talking about today, so I'm just going to skip over that. But if you ever have a chance you can look up orphan versus uncle blocks. Basically, the idea is like, what happens if 2 blocks are created at the same time? How do we handle that? How do we say this block's valid, this block's invalid? So it deals with all that stuff. So those are probably the main differences. And then you can see here, like, so with Ethereum, Ethereum will, every node in the network basically operates as a virtual machine. And so when you have, like, we write Solidity code. We're going to look at an example of Solidity code. When we write Solidity code, it gets turned into Ethereum bytecode. So it gets turned into this bytecode that is then interpreted by the EVM, which is the Ethereum virtual machine. And so it's a process virtual machine. Again, it's getting pretty technical, so we're just gonna keep moving because it's probably out of the scope of like what I think is the most important stuff for today. So now we're on to smart contracts. Any questions so far? Anybody?
Is the logic for the contract in the blocks as well?
Is the logic for so the smart contract needs to get stored in the blocks, and then basically, so like when I call out to a smart contract, basically one node's going to get pinged, the smart contract's going to run, and then every node in the network needs to call that contract. Does that make sense? So in the actual blocks, you will have the contract address and the contract in itself, and then when you call out to the contract, it will run on every node in the network. Does that make sense? Does that answer your question or not really?
Well, because in the Bitcoin blockchain, it's just a long chain of transactions.
Right.
There's no code.
Right.
So in Ethereum blockchain, is the code
Actually stored in the blocks?
Yeah, in the block.
It's a good question. I'm not sure if the address of the smart contract is actually stored in the blocks or if the code is, but we can look that up after if you want to get an answer to that. So it's a good question though. So what is a smart contract? Anybody here familiar with object-oriented programming? Like Java or any of the like Python, for example. So in object-oriented programming, you have a class or an object, right? So you have like in Java, I will create a class, and in that class, I'll have a set of functions, and in that class, I'll have variables. So in Ethereum and smart contracts, you have a very similar arrangement. You have a contract, which is similar to a class. So you can't just run code on Ethereum. It has to live in a contract. So a contract is sort of the building block of being able to run code on the network. Does that make sense? So in a class, you might have public and private functions. So a public function means it can be accessed from any other class that uses this class, whereas a private function means it can only be run within the same class. In Ethereum, you have private and public functions as well. Public functions mean it can be called from another contract. Private functions means sort of like helper functions, and it can only be called from within the same contract, if that makes sense. And one thing that's important to keep in mind is that code can't just be run independently on the network. So you can't just say like, oh, we're going to schedule like, anyone ever heard of a cron job or like a background job? So in programming, you can create code to run sort of asynchronously in the background, not while your user is doing something. So if your user, let's say, clicks a button to do something, and then it's going to require a lot of computation, you can actually have it run in the background while they're continuing to go through their user experience of the application, and then come back with the end result. Whereas in Ethereum, you can't just have stuff running in the background. It has to be triggered by someone or another smart contract. There actually has to be a trigger that says, run this code in this smart contract. So we talked a little bit about the computing environment. We're going to address that. So some applications, they will basically be able to interact with your machine. So sometimes if you use, I don't know, some application, it can actually write data to the disk on your computer, or it can use the file system to get a file. So like when you upload a file, when you upload your resume to a job, for example, they actually have to read the file off your computer. So you would use the file system for that. So their application would have access to the resources on your machine. So if I build a Node.js server or a Java server or a Python server, I would be able to actually interact with the resource on your machine through the operating system. So I would say, hey, I want to read the file system for this file named David Resume, and I would go through the operating system to do that. But basically, with Ethereum, you have no access to any of those resources. So you cannot access anything on the actual machine that's running the Ethereum smart contract code. And so what is available is wallet balances, other smart contracts, you can call other smart contract code from the network, events that get triggered, stuff like that. Does that make sense? So let's just keep on moving. So here's a diagram. I'm gonna walk over. Is this mic on? No, it's on. Can you hear me? Yeah, it's on. All right. So here's the architecture of a traditional software implementation. So you have the client. This could be like your web browser, right? And let's say I click on a button, the client's gonna make a call out to a server, probably through some protocol like HTTP, and then the server is gonna have code that's gonna run, and then maybe it'll save stuff into a database, or it will go read stuff from a database depending on what the user's trying to do. And so then come back, the server will send whatever data needs to get sent back to the client, and it's pretty straightforward. It's very easy to reason about from a developer perspective. You own the whole stack, so it's for debugging. You've implemented all this stuff, so it's compared to over here, it's a lot easier to debug because I already know how my program works and how my system works. Where over here, I have not implemented any of these green dots. Right? This is the network itself. And so with this network, note that none of these nodes are like special in any way. Like when I basically run smart contract code, it will go to one of the nodes, and then the node has to run that code, and it has to notify the network. Every node needs to also run that code, and that's the whole idea of this trust system. That's the whole idea of saying we have a consensus, and if one of these nodes has an issue with the code that ran, but all the others don't, then the whole transaction will fail. And so this is the process here, and this sort of encapsulates all the data storage and server-side stuff that you're used to in a custom over here. Question?
So what's the ratio? What's the ratio of required majority nodes agreeing on something so that it becomes true?
Great question. So every node in the network needs to agree. Otherwise, it's an invalid transaction.
So there's just one who disagrees.
That's it.
Don't you get a split chain and then eventually consensus will pick one as well?
Yeah, so the question was, don't you get a split change and eventually the network will pick one as a winner? So that was coming back to the idea of orphans and uncles, but eventually they'll agree on what is true, what is the valid state, right? So at that point, yeah, they will agree, but so there is splitting of the network, I guess, in that sense. I don't want to get too far into that. I don't want to give any incorrect information or anything like that. So, but hopefully that gives you a sense of like how it's much hard. You can't really trick the system, right? Because eventually it will converge.
What coordinates the network?
What coordinates the network?
Yeah, so how do all the nodes know that it needs to respond to the other node?
So all the how do all the nodes communicate and stuff?
Yeah.
Is that the question?
Yeah.
It's a great question. I don't want to give any wrong answer, so I'm not going to answer that question, but it is a good question. So if you want, we can try to, like, if you approach me afterwards, we can try to look up and see the answer to that. So all right, and then let's see. So now let's look at some actual code. And so this is a very simple contract that you will see used like all over the place. So anybody here ever heard of Open Zeppelin? Anybody know that company? They make basically it's a library of secure smart contracts you can use and then build on top of. So this is a very common contract you'll find. So this contract called ownable, basically the idea of it is when we call a contract, when we deploy a contract, we want to basically say, we are the owner of this contract, and we want to have unique things that we can do that other people can't do. So let's say you want to withdraw money from my contract, or let's say I'm doing an ICO, a token sale, and at the end of the vesting period, I need to send the tokens to someone, right? Because they've gone from they've invested, a year's gone by, and now they should get their investment back. So if anyone could call that method to withdraw, it would be insecure, right? Someone could trick the contract to thinking that the money should be sent when it shouldn't be. So I want to have sort of control of this of that functionality, right? And so the ownable contract would be a way we could do that. So the first line, pragma solidity, this basically says this contract needs to run with a version of Solidity that is greater than to what we specify here, or equal to or greater than what we specify here. So this is 0.4.18. I think the latest version is like 0.4.23 or something like that. But basically, it's saying as long as it's 0.4.18 or higher, this contract will run. Otherwise, whoever tried to call the contract, it's going to be an invalid transaction. So next, we create our contract. In Solidity, you have different types. So you have addresses, you have different types that you can work with. So we're just saying here, this is an address. And we're saying, by giving it public, we're saying that other people can access this address from our contract like this. We are giving this access to other contracts to be able to see, right? And so, but we're not assigning it yet. We're just declaring it. Here we're saying we have an owner that is an address. So if I go to deploy this contract for the first time to the network, we'll look at how in a second I become the owner of it. So next thing here, we're saying we have this event. So an event in Solidity is how you're going to notify, like, let's say I had a website that a lot of times what you'll find is smart contracts in Ethereum is being run, like we said, behind the scenes. Like we pointed here, there's still a client that could still be a mobile web browser, just like it was over here. And so let's say you had a client that had JavaScript, and you ran code, and then this event was fired from your smart contract. You can listen for that event, and then do more stuff on the client side. So that would be a mechanism of how you would communicate with the client. And then here we create a function called ownable. Notice how it matches the name of our contract. So we have a function ownable. It matches the name of our contract. This means it's the constructor function. Anybody here familiar with the constructor function? This means that it can only be called one time. On the deployment, on the initialization of the contract, this will automatically get called, and it will run whatever code you have in this block. When I say block, not like blockchain block, like block of code here. And so in this case, what we're saying is we're assigning this variable we created, owner, to be this thing, message.sender. So message, you can notice, like, where did message come from? Right? That's probably like, how did that get in there? So message is a global variable that has information contained by whoever called the contract. Whoever basically says, I'm calling or deploying this contract, you will have this thing called message, and it's got different properties on it, such as sender, payer is one. So there's a sender, there's a payer, and there's value, how much value is being paid. So here we're saying because the constructor only gets called once, when we deploy the contract, we're saying assign whoever deployed the contract to be the owner. Does that make sense? Any questions? Yeah, whoever. So like I go to deploy this contract, right? It's the first time the contract's been deployed. The constructor function is going to get called, remember? Because that only gets called once.
Okay.
Right? So I go to deploy it, and I've deployed it, and the address is like an Ethereum address. And so basically it's assigning my Ethereum address as the message.sender is going to be the address that deployed the contract, right? So it's assigning the address that deployed the contract to this owner variable that we created up here, right? So that's all we're doing right there. And then, so let's skip this for a second and just come directly down here, right? So if I'm the owner of this contract, I want to be able to transfer ownership to somebody else. Otherwise, what good would it be to be the owner of this contract, right? Because that's like a pretty critical pretty critical piece of functionality that makes this relevant. Otherwise, it just doesn't make sense, right? So, and again, the beauty of smart contracts is you can implement logic to do whatever it is you want. Let's say you wanted to restrict transfer of ownership, you could do that. Let's say you wanted to only transfer ownership in certain cases, you could do that. So like in this case, if someone, so again, because this is public, see how this is public here? This means that another smart contract or someone else can call this function off of our contract. So they can say, I see that there's an ownable contract, I want to call transfer ownership, and I'm going to send in an address of a new owner that I want to transfer ownership to. Remember how I was describing earlier that like, if someone else was able to call this, it wouldn't make sense because it's like, let's say I'm the owner of this contract and you called this and you're like, I want to change the owner of that contract. It just doesn't make sense. And so what we're doing here is we're using this modifier, which we'll now talk about, to basically say, so when someone goes to call transfer ownership, the first thing it's going to see is that there's a modifier. See how we have the keyword modifier here? So there's a modifier attached to it. So it's then going to try to determine which code runs first, the modifier code or our code. And so you see this underscore? This underscore represents the body of the function that uses the modifier. So wherever this is located, this is going to, anybody here familiar with decorators in Python or anything like that? So this would work similarly. So basically, this is going to say, okay, so the first thing is this. So this has to run before, the underscore represents lines 18 through 20, right? And so before lines 18 through 20 run, we have to do this check. So you see the require statement. So there's like 4 main ways in Solidity you can basically assert and say this has to be true in order for me to keep going. If this is false, if this evaluates the false, then the whole transaction will be invalid and nothing will happen. No money, no ether will be sent or exchanged. The only thing that happens is whoever called it will have to pay the cost, the gas cost, for calling the function. Okay. And so here what we're checking is we're checking that whoever called transfer ownership, now we're calling transfer ownership, the message is going to contain information about who's calling transfer ownership. And so now what we're doing is we're checking who called transfer ownership. Are they the owner of the contract? Right? So if they're not, who can tell me what's going to happen? Someone tell me what's going to happen if, let's say, I own the contract and she tried to call the contract. What's going to happen? Nothing, right? Nothing, because this is gonna fail, and then the person, she's gonna have to pay the cost for calling this function. So she's really like not incentivized to do that because there is a small cost. It's a small cost, but and so let's say this passes. Then it's gonna say okay, and it's gonna see the modifier, this little underscore, and now it's saying now I can execute the rest of the code. So now it's gonna come down to line 18. And it's gonna say, okay, we're going to make sure the address is not empty. So we have an address. Otherwise, like this is a very common thing. You want to basically be doing all these as many checks as you can that are reasonable, because if something goes wrong, let's say you weren't checking this. Let's say we didn't have line 18 and we sent it an invalid address. Then it's going to transfer the owner to an invalid address, and then nobody's the owner. So we have a huge bug in our contract. So you have to utilize this. The mechanism Solidity gives you to assert it whenever you can. And so now what's going to happen is, okay, we called it with a valid address. I called it because, remember, let's say I call transfer ownership. It's going to say, okay, this is true. Then it's going to come down here. And it's going to say, we have a valid address because I used an actual Ethereum address. So then it's going to fire this event, ownership transfer. Right? This is where we talked about that event. So now we have like an address, previous owner and an address of new owner. And let's say in the website, we want to display who the owner is of the contract. Right? So now our website's going to be notified, okay, the address changed, and it's going to update to be the new address. And then we're going to make the assign here, and then the transaction will finish. So does that make sense? Any questions on that before we? All right, we got a few questions.
Yeah, why wouldn't you just put line 13, where it says require message sender, just put that on line 17.5? Why would you use the decorator instead?
Great question. So imagine, like this is a very simple example, but imagine we had hundreds and hundreds of lines of code, right? So let's say we had transfer ownership, we had other things we wanted to do, like withdraw or stuff like that, but we only wanted the owner to be able to do that, right? Now we can reuse this all over the place. So now anytime we make a function that we want to do that, we can just add the modifier at the end. And now we don't have to like copy and paste this required here and then there and then down and withdraw and all the other functions. Does that make sense?
Yep.
All right.
So you'd be able to add code to accept ownership as well, right? I mean,
Yeah, I mean, the
Yeah.
beauty of the smart contracts is like we talked about, there are some limitations in terms of you can't access memory on like computer that the Ethereum network is calling out to, but you can make it as customized as you want. The logic itself is up to you to decide how you want it to work. And so that's a good thing and a bad thing. Obviously, it opens up the gateway for like bugs, introduction of bugs, and like the hacking scope increases. So there's a lot more vulnerability when your contract is confusing and has a lot of like complex logic. So we typically suggest like trying to refine your logic so clearly that you can think of like all the different edge cases. But at the end of the day, in software, no one can think of all the edge cases. And so there's definitely tools you can use to help you get there. But hopefully that makes sense. It's like,
So at the moment, if you find a hole in the code of the contract, and then you go in and get all the money out, is that technically a crime against the law?
So, I think part of the problem is that cryptocurrency in general is very global. So it's like who's really enforcing this stuff. So I can't really speak to like regulations or like what would happen. I know that like there was this famous DAO attack where someone drained like a crazy amount of ether from a contract, like $30 million or something, and nobody still knows who it was. So they're just somewhere on a yacht. Probably not in the U.S., but they never got caught, and nobody knows, where they went. So, what would happen? I mean, so here's one thing: is if something like that happens, you can't really undo it, right? Like if like I was saying earlier, if I could undo it, it's not really centralized. You're still just like thinking it's decentralized until something wrong goes wrong, and then now have all the power and I'm the centralized figure. So it's kind of tricky to like figure out how do you undo something. There are some interesting projects out there, like I referred to Open Zeppelin. You should definitely give that a peek. So Open Zeppelin is coming out with this new product that they're working on, where they're sort of trying to create a climate where people will vouch for what is fair and what's not, and the community will converge on it. So it's sort of in a decentralized way, but they're still working through a lot of issues, and like there's some gaps in terms of like how should this work and stuff like that. But they're not the only one addressing that problem, but there's a lot of people who are trying to figure out how to solve that problem. And then further, you can, because remember we talked about how this is very customizable, so you can make it as customized as you want. So if you said something went wrong and immediately I want to be able to just pause the contract so nothing more can happen. Like let's say you had some sort of mechanism, like if you could write logic in that, like if ether was drained, more than X amount of ether was drained in X amount of time, right? Then pause the contract, stuff like that. So you can come up with mechanisms that will help prevent against those types of bad actor sort of nightmare scenarios, but you can't really undo them. So take all the steps that you need to be able to do that. So like an example would be if I'm the owner, I should be able to pause like minting. Let's say my contract does minting tokens. So I create new tokens. So someone will send ether, and then they're participating in our private token sale. So we will mint new tokens. They have to stay in the contract for X amount of time because there's vesting. But let's say I want to be able to stop minting. I can have a function that's like pause minting that only I can call out of the event that something goes wrong. So you have control mechanisms like that. Does that make sense? I don't know if there's another mic, but everyone can just pass that.
So of the functions, how much of it is visible to other people? If you lock it up private, you can lock it up to groups.
So all the functions are visible. They all live on the blockchain, so you can go access them and see like code and stuff like that. Even if you declare something private, it still gets deployed publicly to the blockchain, so you can still go and see it. The only thing that private means, again, is that it's sort of like a helper function, and it can only be called from within the same contract, not from another contract outside. Does that make sense?
Is it compiled before it's pushed to the public blockchain?
question was, is it compiled before it's pushed to the public blockchain? Again, I could probably try to speak to that, but I don't want to give wrong information. So, all right. So I saw it handed all the way in the back. So
It's fine, we got it.
well, all right. Maybe just approach me with questions at the end, and then we can talk. We'll do one more right up here because you're right.
Okay, so I don't know if I'm clear, but let's say like I depend on an external like entity, like a third party.
Mhm.
Let's say I don't know, I have like a will, right, and I want to like give all my ethers to my kids or whatever.
Mhm.
Then how can you trigger this type of smart contract, and how do you protect that, like, veracity?
So there's tools that you can use to actually call a smart contract. So you actually need to either run an Ethereum node. So you can use tools like, let's see, what would be an example, Geth. You ever heard of Geth? It's a Go implementation of Ethereum, so it will let you actually get a node. You basically get an Ethereum node that you can then call directly to the network. So you can use that, or there's, let's see, there's, I think it's JSON RPC. It's an API that will let you go and call out to the Ethereum network. So you can use either of those. And then once you're in your smart contracts, you can trigger an event that your will or whatever application would then be listening for, and go from there. And then there's tools like you can look up Ganache. So the difference between Ganache and Geth, or Parity is another. Parity and Geth are similar. They let you run an Ethereum node. Geth is implemented in Go. Parity is implemented with Rust. And in the blog post at the end here, you'll see that it uses Parity. But then there's also tools like Ganache. It used to be called Test RPC, but they rebranded. And so Ganache will let you actually basically simulate an Ethereum environment without actually running an Ethereum node. So you can look at that as well. Ganache is a useful tool. All right, we're gonna move on, and then questions at the end we can come back to. So here's another contract. There's a bit more going on to it. So this one is super simple. This one is also pretty simple, but you can see there's a little bit more complexity. So the first thing to point out is, again, we have that pragma solidity, right? We already covered what that does. We're importing our ownable.sol. So a .sol file represents a Solidity file, just like a .js file would represent a JavaScript file. And so remember, our contract's called ownable. So we're importing the contract from this file, and then we're saying our contract here, single message, is ownable, meaning it inherits. Anybody familiar with extends, right? Yeah. So this would be like inheritance, and you can have multi-contract inheritance. So we can have this contract inherits from ownable, it inherits from other contracts. You can have a list of contracts that it inherits from. And so just like other programming language, inheritance is a very common pattern. And so the whole purpose of this contract is to basically, we have a message, and in order to change the message, you have to send double what the previous person sent in Ether in order to change the message. It's just a very simple smart contract. So that's what we're trying to do here. So you can see, again, we declare some variables. So we have a string, that's the message, this is the actual message. And in the blog post at the end here, you'll see we actually use this string to display on our website. So if you want to change the string on the website, you'd have to go in and pay Ether and double what the last person paid. And then we'll actually change on the website. And the blog post talks about how to test the contract, which we're not going to necessarily cover, I think, right this second. You can use JavaScript to test, which is really nice. Anybody here heard of Mocha or Chai? So Mocha and Chai makes your job, you can test your contracts in Solidity. You can use Solidity to test Solidity contracts, but it's a little more cumbersome than using JavaScript. And so JavaScript is the preferred method for testing the contracts. Anyways, totally out of scope. So we're gonna keep moving. So remember we talked about the event. So this event is saying our message has been set, and our website's gonna be listening for that event to occur. Here we have our constructor. So typically a constructor will be used to set the initial value of stuff. Like we looked at, we were setting the owner here initially. And remember, the constructor only gets called once. So here when we call single message, when we actually deploy the contract, we're gonna set an initial message, we're gonna set an initial price, and we're gonna set a maximum length that the message could be. And so then we have our set function. So you see how we say external? This means externally, other smart contracts, other people can call this, and you see how we've labeled it as payable. So if you actually want to transact with Ether in a function, you have to mark it as payable. Otherwise, like if we didn't have payable here and we tried to send it Ether and actually do something with it, like send it from person A to person B, it would just fail because the function wasn't marked as being valid for accepting Ether and handling it and knowing what to do. So payable is just like a labeling for that. So here what we're going to do is when set is called, we're going to make sure that, again, message, remember this is a global variable we get when we actually, so I'm sitting here, I call set, right? Basically it's going to look and say, okay, I called set, I declared some value that I was calling set with, right? And it's going to check to see is that value greater than or equal to the current price of the of what had previously been set. And so if it's not, then we're going to return because we know that that doesn't meet the spirit or the intended behavior of our contract. So assuming it is, we keep going. We basically convert this message to bytes. We check the length. We make sure that it's an acceptable string. We can't have someone setting a string that's 1,000 characters long. We want it to limit that amount. So we check for that. And again, all these checks, it's as customized as you want to make it. You can be as strict as you want. But typically for all of these checks, like when you go down and so at the end of the presentation, I have a blog post about the philosophy of smart contract security audit. I'll talk about a security audit at the end of like why it's important and what it means. But the idea is like you need to have a specification that's so specific that you can basically implement it with these checks in code and feel very confident that you're nothing's going to go wrong, right? Because as we talked about, when something goes wrong, it's a big deal. You can't undo it. So those are all really important. And so, so next we're going to change the new price to be double what the old price was, and then we're going to trigger our event message set to let like our whatever is consuming and communicating with our smart contract know the message has been set, and then we're basically going to change the price to the doubled price. And we're going to change the message to a new message. That's all that sets do. Okay, so let's say after 100 people have set the message, and now my partner and I are rich, and we have like thousands of Ether. So we want to go and we want to withdraw those the Ether to one of our Ethereum wallets. So you can see here. So we mark this as external, so somebody can externally call that, and we've used the modifier only owner. Notice how there's nothing about only owner in here except for the fact that our contract inherits from ownable. So basically what it's going to look for is there a modifier called only owner in our contract? There's not. So then it's going to look and say, what contracts does this contract inherit from? And it says, oh, I see this contract has a parent's contract called ownable. So I'm going to now go look in there to see if there's a modifier called only owner, at which point there is. So it's going to make sure that the address that's calling withdraw is the same one that we marked as ownable in our ownable contract. It's the same one that owns our ownable contract. Does that make sense? So now we've got, so if I try to call withdraw and send, because I want to send Ether to my wallet, it will work. If she tries to call withdraw, it won't work because she doesn't own the contract and she doesn't own the Ether. She should not, that was not how the intended behavior was built. So now we require this .balance. This is a variable that we have access to as part of the contract. So when you send Ether to a contract, it actually gets stored in the contract. The contract becomes the owner of that Ether. And so what we're doing is we're checking that the balance of the contract is greater than or equal to the amount that we want to withdraw. If it wasn't greater than or equal to, then we'd be trying to withdraw more than is what is in the contract, and that wouldn't make any sense either. Right? The contract needs to have a balance that's greater than what we're trying to, or equal to what we're trying to withdraw. Right? So after we get through that check, we're going to make sure that the destination is not empty. Right? We're going to say this has to be there has to be an address we're sending it to, otherwise it wouldn't make any sense. And then if so, we're going to transfer the amount that we specify when we call withdraw to our destination address.
So what would happen if I forgot line 29?
So if you're saying you tried to withdraw more than what the balance would be, So that actually might be a good example of a check that may not be that great, because I don't think you can withdraw more than what the balance is of the contract. I think it would just error out, right? So that's my speculation. But I guess this is just a simple example to show like how you have a lot of checks that you can use at your disposal. So there's an attack surface here that we should talk about for a second. So the idea, anybody ever heard of reentrancy? Does anybody know what that means? So I'll just try to summarize it. So because smart contracts can call other contracts, you sort of turn over the context of execution of the code to another contract at some point. So let's say I called withdraw from my Ethereum wallet. Okay? So then that's fine. Another smart contract can also call withdraw. So smart contracts can call functions in other contracts. And so like in this case, if we used a smart contract to deploy this contract in the first place, and the smart contract was the owner and could call withdraw, then let's say this other smart contract called withdraw, and these checks passed, and so it's going to transfer to the other smart contract. Because remember, a smart contract has an Ethereum address, right? So then the amount is transferred to another smart contract. Let's say that smart contract also has a withdraw method, right? That smart contract now manages the code, and we don't know, can we trust that smart contract? We have no idea. So the idea is that it would run withdraw without updating the, without necessarily saying, hey, we're updating that we've taken the money out, and it might just keep withdrawing without us wanting to do that. So that would just be a good example of how this would have an attack surface. But we don't have to get too much into that, but those are important considerations to give when you're thinking, can another smart contract call this code? You don't know what that smart contract's going to be doing, so it's hard. Then the attack surface expands dramatically. Any questions on this contract before we go on? So that gentleman's been trying to ask a question for like decades, so let's get him the question.
Slight exception. So I guess like this code is something that would be run once, but how many contracts are there? And then if there are owners for every contract, how is it decentralized? So if there's like one owner and he or she can call some function that says owner only, how is that decentralized? And then I guess if this is an example of code that you would run for a contract, what's an example of code you would run as a subscriber or participant on Ethereum? Like what exactly are you modifying?
Okay, so I wasn't trying to follow the last question, but the first question meaning, it can only be called once. That's only the constructor. So you can call any of the other functions as many times as you want. Only the constructor is going to be called once. That's it. And then like set or withdraw in this case, I can call as many times as I want. Does that make sense?
So set can be called by anyone. Doesn't have to be.
Yeah, in this case, set can be called by anyone because why would I want to restrict you from being able to set the string? That was the whole purpose. Because you should be able to change the string on my website and send it ether, right?
Yeah, I guess I mean so in that case I send you ether, right? So only you can like withdraw that ether?
You don't send me ether, you send the smart contract money. And then the smart contract will decide what happens with that ether based upon the rules that were set out in the smart contract.
Which you wrote.
Which I wrote, but let's say, so I guess, I might be the author of the smart contract, but the smart contract might run code that decides on certain things that have nothing to do with it, right? So while I might have been the coder that actually created the contract. So like, I'll give you another example. So we talked about Open Zeppelin, right? So they're coming up with a system that basically lets people, when they find issues, basically decide like which versions are valid and which versions aren't valid. And then also, like if there needs to be code that should be changed, what should be the correct change? And in doing that, there's rules set up around like token exchange and stuff like that. So, I mean, that's just one simple example, but just because they're the author of that contract doesn't mean that they have the decision-making power. It's the smart contract itself that makes the decisions what happens. Does that make sense? And in this case, if I couldn't protect withdraw to be me being able to withdraw it, then the whole purpose of the idea of the smart contract would be it just wouldn't make any sense, because then you could withdraw the money that I earned by creating the website that you're supposed to send Ether to, right? So I guess that maybe this isn't the best example of a decentralized. I still think it's a good example, but I see your point there. But I think the only purpose I was trying to get at of only owner is to draw attention to, you can make this as customized as you want, and you have all the control, right? And when I say you have all the control, it's not over, like, it's not making it centralized, it's just that you can implement it however you want.
Bit of a funny one, I'm not a coder, right? But if I'm just looking at this in relation to vulnerability, right? So obviously it goes on the blockchain, so no one can kind of mess with it, otherwise so other people can see it. Man in the middle attack isn't really valid. But just let's say this gentleman here, he talked about when I leave your Ether to your ETH to your children, and then debts and marriages are vital department, what do you call it, in San Francisco gets hacked, to go to the smart contract and say this person's dead, but they're not. Where do you see a kind of validity of where like I see security vulnerabilities, not in the smart contracts, but the stuff that feeds into it. So I'm more like just making a comment, but
It's a great comment. So I think the important thing to remember is it's all about specification. So when you actually go and you would create your smart contract, you would try to anticipate what happens if someone tries to send us something that's invalid, right? Stuff like that. So in that case, yeah, it's kind of hard to think about, like, I guess that use case from like what would we do. But just remember, you have control over trying to anticipate those things. So we talked a little bit about a security audit. So the idea is after you have a smart contract that's been created, you have to have people who did not write the contract just rip it apart from like a code review standpoint. Basically, you're trying to find security vulnerabilities, you're trying to find bugs in the logic like that, for example. And that's where you would probably catch a lot of that stuff. So anyways, here are some good resources. I think we're out of time, so I have to wrap up. The first one is our blog post on how we built this Ethereum dApp that you just looked at, and you can actually see the website, interact with it. I think we started with like 1 cent in terms of the price to change the message, and now it's up to like $15 or something. But it's a very basic smart contract. The second one talks about the philosophy of security audit, why it's important. Definitely give that a read. And then the following two is just the Ethereum white paper and the crypto kitties. So feel free, we'll leave that up, take a picture if you want, but they're all great resources. So thanks again for coming. Hope you got something valuable out of it. And sorry if I didn't know everything, but